Hello and welcome back to Neural Data Science. Today we're going to learn about plotting with Matplotlib, a package in Python. Questions we'll address are how can I plot my data and how can I save my plot for publishing in formats such as PNG or PDF. Our learning objectives are to create a time series plot showing a single dataset, to create a scatter plot showing relationship between two datasets, using methods to plot directly from Pandas data frames, and how to customize basic features of a plot, such as axis labels, titles, colors, and line styles. All right, so we'll be using a package called Matplotlib. It's effectively the core plotting and data visualization package in Python. Many other packages that do plotting in Python use Matplotlib for kind of their back end. So they call Matplotlib routines to do their plotting. It's not the only package, and there are many others, including Seaborn, which we'll learn about later, and a variety of others like Altair, ggpy, bokeh, and plot.ly. Some of the others are actually built on top of Matplotlib, as I say, but others are independent. Regardless, Matplotlib is the best one to start with because it is the most commonly used and the most powerful, and because it connects to most of the other major scientific Python packages. Matplotlib is a very mature Python package. It was first released in 2003, and it's been continuously updated since then. There's lots of documentation available online for free, help pages, manuals, books, all that kind of stuff. So the history is that Matplotlib's original developer, the late John Hunter, was a neuroscience PhD student, and he wanted to plot electrocorticography data. So this is data recorded directly from the surface of the brain. Hunter originally designed Matplotlib to emulate the plotting abilities of MATLAB, but in Python. MATLAB is a commercial programming language and environment that's used widely in scientific and engineering domains. But because it's a commercial programming language, that means that there's a company, the MathWorks, that oversees and controls the development of MATLAB. Unlike Python, which is open source and there's more flexibility. So developers can write code for MATLAB, but they're kind of constrained by the decisions of the company itself. So Hunter decided to switch his work over to Python as an open source platform, but he wanted a plotting interface that was similar to what he was familiar with in MATLAB. And so that's why it's called Matplotlib. The mat part is because it's trying to emulate MATLAB functionality. So we've previously covered how to import Python packages using the import command and assign the package to an alias using as. So for Matplotlib, the convention is that we're going to import matplotlib.pyplot. So this is a little different from importing, say, pandas, as we've seen already. Matplotlib.pyplot. So we're actually importing one part of Matplotlib, pyplot, which is the central module that's used for plotting. So you just get used to typing this in, import matplotlib.pyplot as PLT. PLT is the common alias for Matplotlib's pyplot plotting functions. So now to generate a plot, first we're going to enter some very simple data, 4 data points in fact. So time equals and a list with the values 0, 1, 2, and 3. And then position as another list with the values 0, 100, 200, and 300. So this hypothetical data is for tracking the position of an object that's moving over time. So over 4 time points, its position changes in some arbitrary units from 0 to 100, etc. And then the plot command is just plt, that matplotlib alias that we imported up above, dot, and then plot. Very simple. And then we give it the x and the y data that we want to plot on the x and the y axes. And since we're plotting, it assumes that we're going to give it data, the first 2 arguments to plot. We don't need kwargs, we don't need keywords. We just give it the variable names, so time and position. Run that, and we get a lovely straight line. And you can see that on the x-axis, the values go from 0 to 3, corresponding to time. And on the y-axis, they go from 0 to 300, corresponding to the range of values we gave it for position. You can also see up at the top that there's some text here, matplotlib lines.2d at 0x7fbe, blah, 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 blah. That's a bit of extra text that Matplotlib likes to generate when it generates a plot. It's part of the result of the plotting command. And there's an easy way to get rid of that because it's just kind of distracting text that we don't really need. And that's to run a plt.show command after running your plot.plot command. So we'll do that again, plt.plot time, comma, position, and then plt.show. Now we get the same plot, but no confusing, distracting code at the top. So it's a good habit just to get into running the plt.show command at the end of any cell in Jupyter where you're running a matplotlib plot command. So lovely graph, clean, simple, axes have the range on them, but there's no labels, so we don't know what the x and the y values represent. And that's a pretty important thing whenever you're doing a plot, is to make it very obvious to the person looking at the plot what you're plotting and how to interpret the plot. So axis labels and eventually a title are really important things. Pretty easy to do this in Matplotlib. So again, we're going to run plt.plot time, comma, position. And then we run a series of extra commands to add things to the plot. So plt.xlabel, and then time, and it turns out time is in hours, so we'll say time in hours. And correspondingly, plt.ylabel, position. And you saw there that I accidentally typed plot.ylabel originally. It's a really easy trap to fall into because our brains naturally sort of want to spell things correctly. And very often when people get errors, it's because they accidentally type plot instead of plt. So just watch out for that. plt.show is our last line in our cell. And now we get position in kilometers on the y-axis as their label, and time in hours on the x-axis. Turns out it's also really easy to plot data from Pandas data frames using Matplotlib. So let's import Pandas as PD, our standard alias. And then we'll read into a data frame called df pd.read_csv. So this should be familiar from the Pandas lesson that you've already done. And we're just going to read our gapminder _GDP Oceania data. That's a .csv file. And we're going to set the index column to equal country because we know that's how the data is indexed. Run that, see what the data looks like by just running df. And we see the entire data frame is just 2 countries in the Oceania region, Australia and New Zealand. So it's a simple data set for plotting. We don't have a lot of countries that we need to worry about. So how do we plot directly from a Pandas data frame? Well, it turns out Pandas data frames have a method called .plot. And that .plot method in Pandas is actually just calling Matplotlib's plt.plot. But it's simpler just to say df.plot. So we can say df.plot and then plot.show. There we go. So we've plotted the data frame, but maybe in the not the most straightforward or interpretable way. So we can see we've got Australia labeled on the x-axis and then a label for country for the entire axis. So that's actually nice. Pandas is automatically adding that X label without us telling it. And it did that because it read the index column and it read the label for the index column and just pulled that out. It's showing us Australia. Presumably New Zealand, the other country, is on the other end, but it's not showing us that label, which is a bit unfortunate. And as well, what it's doing is it's plotting lines connecting the 2 countries and separate lines for each column. So remember, each column is GDP per capita. This is probably not the way that we would want to represent this data. Probably what we want is year along the x-axis and separate lines for each country so that we can track the GDP of that country over time. And we'd also like to have a label on the y-axis saying GDP. So how do we do that? Well, it turns out that when you run .plot on a data frame, Pandas assumes that your columns are different categories that you want to plot as separate lines. And it assumes that the index column is what you want on the x-axis. But it's actually easy to override this in the case of a data set like this, where we actually want the columns along the x-axis. And that's using an operation called transposition. So this is a fundamental sort of mathematical matrix operation. But very simply, you can think of it as swapping the rows and columns in a data frame or any other sort of 2-dimensional matrix. So in other words, the columns become the rows and the rows become the columns. And in Pandas, we do that with a .T method. So df .t, it's actually an operator, not a method. The difference is that .t, we don't give it parentheses. It doesn't take any arguments. It doesn't even take empty arguments. As an operator, we just do .t without the parentheses, and then a dot, and then plot. So we're going to transpose the data kind of on the fly. We're not actually modifying the stored version of df. We're just applying the transposition on the fly and passing that transposed data into .plot. And then plt.show. All right. Now we've got something that looks a little more like what we hoped for. So we've got GDP per capita in the years along the bottom, so time on the x-axis, GDP still on the y-axis. We still haven't got a label, but now we have separate lines for each country, Australia and New Zealand, and Pandas/Matplotlib has kindly generated a legend for us with those labels, which is really nice. And just to make the point that when I applied .t, I didn't actually change the data frame. You can see the original stored version of the data frame in df hasn't changed. So again, we're just running that transposition on the fly for the purpose of plotting. We're not modifying the original data frame. Now, one other thing that we might want to do is change the labels on the x-axis, so the column labels, because right now they all start with GDP per cap. That's not actually what we want here. Those are just years, actually, on the x-axis, and then GDP per cap is on the y-axis. So let's strip the GDP per cap underscore from all of the column names. It's quite easy to do. You can batch change column names in Pandas. So df.columns refers to all of the columns in Pandas. And you can see I'm putting that on the left side of assignments. So I'm modifying the columns. And I'm going to say that the new value of df columns is equal to df.columns, so the original value, .str.strip. So we're applying a method in Pandas, and it's actually a little complex because Pandas has kind of a submodule called str for working with strings, and then it has a module specifically, a method specifically within that string module for stripping off characters. The reason it's organized like this is that stripping doesn't make sense for numerical data. It only makes sense for string data. So it's sort of nested under strings, so you can only apply it to strings. Okay, and then we just give it the text that we want to strip from all of the column labels, which is GDP per cap underscore. And then let's see what df looks like after I run that. So we've modified df, and now those column labels are just numerical. All right, so now if we run the same plot command as we did up above, so df, pass that through transpose and plot, and then plt.show. So now we've got our x labels just the way we want them. GDP per capita here. We don't have x and y axis labels yet, but that's okay. So we'll get there. And again, we can look at the data frame. It's not changed. We can customize the plot appearance by passing what are called keyword arguments, or kwargs. These are basically arguments to a method or a function, where rather than just giving it the actual value that you want to pass as an argument, you give it a keyword like color equals, so it knows what argument or what property you're trying to pass, and then you give it values after that. So in this case, we want to pass a color kwarg to df plot. So df.t.plot, and then we say color equals, and then we give it a list with as many colors as we want. If we were only passing one color, it wouldn't have to be a list, but because we have two different lines that we want to color, we're going to give it two colors. And those colors are going to be red and blue. Most of the color names you can imagine, you just type in literally orange, yellow, green, whatever. There's also a whole bunch of other more sort of fancy variations on color names. And if you just Google like Matplotlib colors, you'll get a list of all of those if you want to get fancy. plt.show. So same plot, but now we've colored the lines. And it just applies those colors in sequence to the labels or the categories in the data. The next thing is that we can select a subset of the data frame. If we don't want to plot both countries, we can say df.lock. Remember, that's how we select rows and columns in a data frame. And in this case, we're just going to say Australia. We don't have to give it, that's a row in the data frame. We don't have to give it columns if we want to select all the columns. and then pass that to .plot, and then plt.show. And because we only passed it one row, that's essentially a pandas series, we didn't have to apply the transposition because the .plot method is smart enough to know that if it's one-dimensional data, then it should put the sort of long axis along the x-axis. So we have one row but lots of columns, so put columns on the x-axis. All right, let's customize this plot and change both the color of the line and the line style. So we're going to make it a dashed line instead of a solid line. So df.lock, square brackets, Australia, .plot, and then again a keyword arg for color equals y. So I'm going to make it yellow. Turns out with common color names you can abbreviate them just to the first letter, or I could type out the entire yellow. And then a second keyword argument for line style equals dash dash. And you'll notice here that because I'm only passing one country, Australia, I'm not passing lists to color and line style, I'm just passing single values. And plt.show. Correct my typo. There we go. Turns out yellow was not a great color choice because it's actually really hard to see. So let's change that to orange. There, much better. All right, the next section is types of plots. And I guess what I missed is how to label the axes, but we covered that up above. So let's do this again, df.lock Australia.plot color equals, and let's do something different this time, like sky blue I think is a valid color. And line style, I can give it a colon, which will be a dotted line. Oops. And then plot.xlabel equals, oh, no, like that, xlabel, and then the argument is the label we want, so year. And plt.ylabel is GDP per capita, and then plt.show. And again, I made a typo. Okay, so now I have a dotted line, because I used the colon as the line style. It's sky blue, which is a little pale, maybe not the best color, but just to illustrate that there's lots of colors available. Year is a label on the x-axis and GDP per capita on the y-axis. Awesome. So we can generate different kinds of plots. What we just saw was a line plot. So it was plotting the data points, but it didn't show individual points. It just connected them with a line from point to point. We can get different kinds of plots with the kind kwarg. So here I'm going to say df.t, so again transposing because I'm going to pass it the whole data frame with both countries, and then plot, and now I'm going to say kind equals bar. This is going to give me a bar graph. And then plt.ylabel GDP per capita and plt.show. There we go. So now you can see that what it's done is plotted a bar at each year and different colored bars for each country. So blue for Australia, orange for New Zealand. And we can sort of, this bar graph format allows us to make pretty clear sort of year by year comparisons as well as seeing the trend over time. Whereas if you go back up, when you look at a line plot, you're focused probably more on kind of the trends over time, although you can see where they diverge more. So over time, they get more different in their GDP. So it's just a different way of visualizing the data. The line graphs tend to sort of treat the variable along the x-axis as continuous, and you can see sort of trends over time. Obviously, you can see that with a bar graph, but the bar graph sort of focuses more on each year as a separate category with data and no years in between, so it doesn't sort of connect the dots and interpolate between them. There's other plots types as well, such as scatter plots that we'll see below. And one thing to note is that some of the plot styles can be defined as keyword arguments to .plot, and then in other cases there is sub methods essentially to .plot. So what we're going to see for the scatter plot is .plot.scatter. Sometimes both are available, and here we're just showing you the .scatter format to get used to the fact that there are two options, keyword arguments and these sort of sub-methods. So since Australia and New Zealand are in the same region in the world, they engage in a lot of trade with each other, so it's likely that their GDPs are correlated with each other. In other words, as Australia's GDP goes up, so would New Zealand's. If Australia's goes down, New Zealand's would go down as well. One way of looking for correlations between different variables or different levels of a variable would be to generate a scatter plot, where rather than putting year on the x-axis and GDP on the y-axis, we plot one country's GDP along the x-axis and the other country's GDP on the y-axis. And we kind of lose the year information explicitly, but we're still plotting all of the data points for year. So you'll see what that looks like when I run it. So df.transpose.plot.scatter. And then I'm going to tell it explicitly with keyword arguments that I want x to be the data from Australia. And I want y to be the data from New Zealand. And I'll add a y label of GDP per capita. Now, this is what I have here. That's maybe not the best y label because, in fact, the y label is New Zealand, and the x label should be Australia. And a new one, plot.title, is GDP, well, we'll use what's up there, relationship between GDP of Australia and New Zealand. And finally, plt.show. All right, so you can see with the scatter plot, we didn't ask for a line plot, we asked for a scatter plot. So rather than lines connecting the dots, we get the individual dots. So the first value is the corresponding values for New Zealand and Australia in a particular column, so in a particular year. So each of these dots represents a separate year. It's not telling us which year is which. In this case, we're less concerned about which year is which, so much as just how the two values relate between the two countries. And you can see that there does appear to be a correlation because it's positive, because over different values, whatever Australia's value is, New Zealand's is quite similar, and they kind of increase in parallel with each other. Okay, so now we get to the exercises. As always, I invite you to pause the video, work through these on your own, and then we'll work through them together. All right, so our first exercise is the expanding wealth gap. Fill in the blanks below to plot the minimum GDP per capita over time for all the countries in Europe. Modify it again to plot the maximum GDP per capita over time for Europe. So, since it's fill in the blanks, I'm going to copy and paste the code, then modify it. Okay, so the first line is data underscore Europe equals PD read CSV, and we read in the Gapminder Europe data. Next line is data Europe dot something dot plot label equals min, and we want a method to find the minimum value. Well, you may remember that that is simply .min, parentheses, because it's a method. And likewise, what's the method to find the maximum value? Well, it's .max. The only other blank we need to fill in is this last line to show the plot. Last line in our Jupyter cell for plotting is always plot.show. There we go. Another nice thing is that the ticks on the x-axis are now rotated 90 degrees. And that was achieved by this line, plot.xticks rotation equals 90. We could change that. We could make it 45 degrees if we want. So rather than stripping off the labels in this case, we just rotated them so that they don't overlap. Another trick you can use, especially if your labels are necessarily sort of long and have this tendency to overlap. Another line is plot.legend lock equals best. That is kind of optional because in this case, that's probably where the legend would end up anyway. But you can actually use that to guarantee that your legend isn't overlapping with your data. Matplotlib will automatically find the best location that doesn't overlap or overlaps the least with your data. You might note that the variability in the maximum is much higher than that of the minimum. In other words, over time, the maximum goes up, so rich countries are getting richer, but the minimum seems to stay pretty flat. So it seems like poor countries kind of stay poor, and the minimum GDP in the poor countries doesn't go up. So there's this increasing wealth gap between rich and poor countries. We can visualize that by plotting the max values and then also printing the IDX max of the different countries and the IDX min. So remember, those tell us the labels corresponding to the minimum and maximum values. So what we see is that for the first sort of half of the time period that we have, Switzerland is the richest country, and then Norway becomes the richest country. Whereas for the poorest countries, Bosnia and Herzegovina is the poorest country for about 20 years, and then Albania is the poorest country. So this is really just showing how you can use a graph or a plot to understand your data a bit better, and then use other Pandas commands to dig into the data and try and understand those patterns in more detail. Our next exercise is called More Correlations. So this short program creates a plot showing the correlation between GDP and life expectancy for 2007. Using help and other resources, explain what each argument to plot does. Okay, so we don't even have to run it at this point. We just want to try and understand what it's doing. Well, actually, we may not need that much online help because we've already covered most of this. So data all equals PD read CSV. So we're reading in the Gapminder all data set. And then data all.plot, kind equals scatter. So we're going to generate a scatter plot. And again, we can use the kind kwarg, or we could say .plot.scatter. We're assigning GDP per cap in 2007 to the x-axis and life expectancy in 2007 to the y-axis. So it turns out this Gapminder all data has both GDP and life expectancy data in it. And then S equals data underscore all, and it says pop 2007 divided by 1e6. So that's 1 times 10 to the power of 6, plot.show. So the only one that we really don't know what it's doing is the S kwarg. And maybe what we could do is run it and see if we can infer what S is doing just from running the code. That looks pretty cool, huh? So you can see that the dots are different sizes. So maybe S is a keyword argument that determines the size of the data points. So basically, we're plotting the relationship between GDP per capita in 2007 and life expectancy in 2007. So we're taking 1 year in the data set and doing a scatter plot, mapping essentially the wealth of the country against the life expectancy. And as you might expect, life expectancy in poorer countries tends to be lower. Life expectancy in richer countries tends to be higher, although it's not a sort of a linear correlation. You can see that very quickly with increasing wealth, life expectancy goes up quite a lot, but then it kind of plateaus. So when we go from 10,000 to 50,000, there isn't really a huge increase in life expectancy relative to going from something that's close to 0 up to even 5,000 or certainly 10,000. And then the size of the dots is now showing us population divided by 1 times 10 to the power of 6, which is basically just scaling the population in a certain way. So that's basically allowing us to see life expectancy, GDP per capita, but also the population size, just to ask, is that another factor? So now we can get 3 dimensions or 3 different variables in our scatter plot, one on the x-axis, one on the y-axis, and one is determining the size of the points in the plot. So this is a nice trick. Color is another way that you could do this, or shading or intensity, to add a third variable to a plot when you only really have 2 dimensions, x and y, to work with. Our last bit is saving your plot to a file. So if you're satisfied with the plot you see, you may want to save it to a file so that maybe you could use it in a paper that you're writing, or a publication or a website. So there's a function in matplotlib.pyplot that accomplishes this, and it's plt.savefig. And the argument to it that you have to provide is the name of the file that you want to write out. You add an extension at the end, like .png, and Matplotlib will determine just from that extension what format to save the file in. So I say .png, it'll save a PNG file. If If I say .jpeg, it'll save a JPEG. If I say .pdf, it'll save a PDF. You can Google the help for plot.savefig and see all the different image formats that Matplotlib will save as. There's quite a few. Pretty much anything you can imagine wanting, it will do for you. So just to show you this in action, we're going to do df.t.plot. So this is our Oceania data. Kind equals bar. Why not? And plt.savefig my_figure.png, and then finally plt.show. One important thing, again, plt.show, oops, and I made that error I told you that is common to make, which is plot instead of plt. One important thing is plot.show should be the last command in your Jupyter cell. I said that before. That's particularly important here because if you run plot.show before plot.savefig, it won't actually save the figure because it's already showing the figure in your notebook. And at that point, it kind of dumps it and it doesn't have a figure to save anymore. There you go. So we have that here. And I'm going to switch to the file view on CoCalc. And you can see now that I actually do have my figure.png in there. When I click on it, that's the same figure. So it's stored as a file. And with CoCalc, switch back to files. If you wanted to actually get this file onto your own computer, you could click the checkbox there and there's a download option and you could download it to your computer. Okay, so this brings us to the end of this lesson. To summarize our key points, Matplotlib is the most widely used scientific plotting library in Python. Methods allow you to plot data directly from a Pandas data frame with df.plot. It's common to need to select and transform data before you plot it. So we saw the transpose transformation there. Many styles of plot are available, and there's a Python graph gallery that you can check out for more options and inspiration. And it's possible to plot many data sets together, as you saw, and even beyond just plotting something on the x-axis, something on the y-axis, we can use additional things like the size of the dot to plot another variable, or potentially the color or shading of a plot element. So there you have it. Thanks for watching, and we'll see you next time.